Okay, here is the condensed version of section 3.1 from OpenStax PreCalculus. In this section, we talk about complex numbers. What a complex number is? It's a number that can be written in this form, a plus bi, or really that is written in this form. The value of a is what's called the real part, the value b is what's called the imaginary part, and a and b are real numbers. So an example of a complex number would be something like 3 plus 2i, or 7 minus 5i, or 4 plus a half I, or something like that. That's what a complex number is. A complex number comes from the need to take the square root of negative numbers. Because right now the square root of a negative number like -4 is undefined. I don't have an answer. You can't take the square root of a negative. It's probably something that's been preached to you a time or two. But in fact, by changing what we think of as a number, we can answer that question. And really all we have to do is introduce one new symbol and then a new way of thinking about dealing with these numbers. And that new symbol is this I right here. It's the imaginary unit. It's this I right here. And it's defined to be the square root of -1. And so if you take this definition right here and you square both sides of the equation, you'd get here. You'd square this side, and over here the square root and the square cancel, and you get here. These are equivalent statements, and you can kind of think about them as the definition of I. Maybe I'll even write that. Definition of I are these guys right here. And really, if I'm trying to give you a shortcut, a way to do all this, all you need to know is that the people, the person, whoever invented, came up with complex numbers, was very clever in terms of how they wrote it. And things work out nicely. Things work out how you would like them to work out. What you will be doing is applying these definitions and otherwise treating the I as a variable. Treat the I like you would the X. Like an X. And I'll show you what I mean by that. So first of all, a little bit of vocabulary. A complex number will be written in this form, so your answers will look like this. A complex conjugate is a lot like a complex number. You just change the sign on the imaginary part. So if I have a complex number like 3 plus 2i, that 3 plus 2i is a complex number. It's complex conjugate is 3 minus 2i. And then you're like, wait a minute, but what if it were 1 minus 4i? Then what would I do there? It's already negative. No problem. Its complex conjugate would just be 1 plus 4i. Because really, this is in a plus bi form. A is 1, b is -4. And so if you switch it from a plus bi to a minus bi, you have 1 minus -4i. And minus -4 is the same as plus, so we get here. So there's a little bit of definition. Graphing complex numbers. Turns out that these are two-dimensional numbers. We can't plot these on a number line like we could with real numbers, but I can still graph them. All we do is we graph the real part on the x-axis and the imaginary part on the y-axis. So a number like 3 plus 2i would appear right here. And a number like 1 minus 4i would appear right here. Note that on the real axis I got a 1, and on the imaginary axis I got a -4, so I got 1 minus 4i. That's it. That's how you graph complex numbers. The most important thing to note is that they're two-dimensional, so I can't just put them on a number line like I can with real numbers. The main topic for this section is adding, subtracting, multiplying, and dividing complex numbers. I'll whip through those real quick. If you're adding together two complex numbers, there's a complex number, and there's a complex number. And you're adding them together. Note the unnecessary parentheses. These are there just to really make you think of this as a single complex number. Not a sum of two numbers, but a single complex number. Just like you think about a fraction like 3/5 as one number, not a number 3 divided by another number 5. We can think about this as a single number. But the good news is that when we're adding these together, it works just as though these were two separate numbers. Just as though you were treating the I like an X. If this I were just a variable and I asked you to add these together, you could do it. You'd say, well, first of all, these parentheses are totally unnecessary because I'm just adding here. And when I'm adding and I have a variable, I combine like terms. The 3 and the 1 gives me a 4, and the 2i minus 4i nets out to -2i. It'd be nice if that's how you added up complex numbers. In fact, you do. That's exactly what you do. This is adding. Okay, what about subtracting? Well, it turns out that subtracting is not much harder. Let's do the same problem, 3 plus 2i, except now we'll subtract 1 minus 4i. Note now the parentheses are important, because without the parentheses I'm only subtracting the 1, not subtracting this entire number. To subtract the entire number, I need the parentheses, but the operations, the way I actually go through and subtract these things, I can almost treat it as though these were all variables. So I got 3 plus, I could get rid of the parentheses by taking this -1 and distributing it through. Getting minus 1 plus 4i. Right? If you were adding these together and these were variables, you'd be like, I want to combine like terms, but I can't do it because of the parentheses. So let's first get rid of the parentheses by distributing this negative through. Then let's combine like terms. I got a 3 and a -1, combine those, you get a 2. I got a 2i and a 4i, combine those, you get a 6i. Wouldn't it be nice if subtracting complex numbers were that easy? In fact, it is. This is your answer, 2 plus 6i. Note that you might go through those steps and write 6i plus 2. Which is fine, it's equivalent to your answer, but it's not your answer because this is not in a plus bi form. Remember, a complex number is supposed to look like this. This doesn't look like that. So my answer would be this thing up here. What about multiplying? Here's a complex number. Here's another complex number. Let's multiply them together. Well, if these were variables, I'd FOIL. Yeah? Well, why don't you FOIL then? 3 times 1 is 3. 3 times -4i is -12i. 2i times 1 is 2i. And 2i times -4i is -8i squared. Oh, and now I can combine like terms. -12i plus 2i is -10i. But wait a minute, I got a problem. What I have down here is not a complex number. This is not a plus bi. It's a plus bi plus ci squared. There's a problem here. This cannot be my answer because it's not a complex number. Fortunately, there's a solution, and the solution lies on this page, right here. I squared is equal to -1. By definition, I squared equals -1. Anytime you see an I squared, you can instead write -1. Hey, I see an I squared. You telling me I can write a -1 right here? Sure can. 3 minus 10i minus 8 times -1. But wait a minute. -8 times -1 is just positive 8. If I had a positive 8 here, I could add it to this 3 here to get 11. 11 minus 10i is exactly the product of these two things. There's an interesting geometric interpretation of multiplying these guys together and having them all plotted here, but I'll do that in a different video because that would take me a little while. Finally, I guess not the last, the second to last thing I want to do is dividing. Let's divide these same two complex numbers. Actually, I'm going to get clever here. I am going to divide, I'm going to do a slightly different problem. I'm going to do 3 plus 2i divided by 1 plus 4i. Change the problem a little bit. I know I've been dealing with 3 plus 2i and 1 minus 4i, but for this example, I chose to change the numbers. Just giving you an example so I can make it whatever the hell I want. 3 plus 2i divided by 1 plus 4i. How would you do a division problem like this? Step 1, write it as a fraction. I already did step 1. I already wrote it as a fraction. But if I just asked you to divide 3 plus 2i by 1 plus 4i, you'd have to do step 1 and write it like this. Step 2, take advantage of the fact that you have a fraction. Fractions have this great property that you can multiply the top and the bottom of the fraction by any number you want without changing the value of the fraction. So if you feel like multiplying the top by 7 and the bottom by 7, you go right ahead. That won't help you. But what will help you is to multiply the top and the bottom by the complex conjugate of the bottom. Why? For now, just trust me. I'm going to take this fraction and say because it's a fraction, as long as I multiply the top and the bottom by the same thing, I'm not changing the value of the fraction. So what I get when I multiply these two guys together here will be the same as what I started out with in red. But the nice thing, it turns out that complex conjugates have a really powerful property that I haven't described to you yet. It turns out that anytime you multiply a number by its complex conjugate, you always end up with a number, with a real number. All of the i's magically go away. What do you mean magically go away? Well, just watch. It's not anything new from this section. It's just a property of multiplication. If I were multiplying these together, well, I guess I'd have to multiply the tops together and the bottoms together. Note, I was kind of clever. I knew that I'd have to multiply 3 plus 2i and 1 minus 4i later on. And I said, this is the quick version of this video, so I don't want to give another example on how to multiply complex numbers. Why don't I redo this one? 3 plus 2i, 1 minus 4i, I already figured out was 11 minus 10i. Had you not already done that, you'd have to FOIL out the numerators here. What about the denominators? If I were FOILing out the denominators, 1 times 1 is 1. 1 times negative 4i is negative 4i. But look, 4i times 1 is positive 4i. How convenient. 4i times negative 4i is negative 16i squared. But note what happens here. The negative 4i and the positive 4i cancel each other out, so those i's go away. And this I squared I can get rid of because, again, I know I squared is negative 1. So all of the i's in the denominator are gone. That was not a coincidence. That'll happen anytime you multiply a number by its complex conjugate. So really what I have here is 11 minus 10i divided by 1 plus 16, aka 17. These canceled out. Negative 16i squared is negative 16 times negative 1, which is positive 16. Positive 16 and one more is 17. So I'm done? Nope. Why are you not done? Because this ain't a complex. This is not a complex number. Complex numbers must be written in this form. This is not written in that form. However, this is equal to this, and this is in that form. If you have trouble seeing why this is equal to this, well, I guess 10/17 I is the same as 10i over 17. And then you got a common denominator so you can add up the numerators. Oh, that's not equal. That should have been a minus sign in there. There we go. This is equal to this. You subtract the numerators. 11 minus 10i is exactly what you have here, and you write your common denominator once, you get the 17. The advantage of this form is now it's a complex number, so I can call that my final answer. Last thing I want to do is look at powers of I. For powers of I, what you notice is that you get this nice little pattern that I to the first power is just I to the second power is negative 1, and that's by definition. I to the second power equals negative 1. I to the third power, you can get kind of clever and say I to the third power is I to the second power times I. Right? I to the second power times I to the first power would be I to the third power. But I to the second power I know to be negative 1. Maybe I'll write this all out. So this is I squared times I, which is equal to negative 1 times I. And if I could just treat I like a variable, I would say negative 1 times I is negative I, and you can. I to the third power is negative I. So then what's I to the fourth power? Well, I can do the same thing. I to the fourth power, for example, is I squared times I squared. And that's negative 1 times negative 1. And negative 1 times negative 1 is positive 1. Oh, I'm still not quite seeing this pattern you're talking about. Well, think about I to the fifth power. I to the fifth power is I to the fourth power times I to the first power. Why did I write this as I to the fourth and I to the first? Because I to the fourth is really nice. It's just 1, and multiplying by 1 is easy. 1 times I is just I. So what happens is things start to repeat. You get I to the first power is I to the second power is negative 1, I to the third power is negative I to the fourth power is positive 1, and then you kind of just keep going around this circle. So I to the first power, second power, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th. If you ask me I to the 15th power, I can count my way around and get this negative I right here for my answer. If you ask me something like I to the 378th power, you could still count your way around this circle, although it might get a little bit tiresome. But what you could also do is note that any I to the fourth, any group of 4 of those i's, if you have I to the, I've already forgotten what number I said, but let's go 409th power to make my life a little bit easy. I to the 409th power is I times I times I 409 times. Sounds like a lot of work. But I can think about that as I to the fourth power 102 times. And why did I think of, well, not quite, times one more I. I to the fourth power 102 times is 408 of those i's, and then I to the first is the 409th of them. Why did I write it like this? Because I to the fourth power I figured out as 1. So any multiple of I to the fourth power is also 1. So this is just 1 times 1 times 1, 102 times, which is just 1 times I. Turns out that I to the 409th power is just I. Anytime you're multiplying powers of I, you can figure it out either with logic like this, or if the exponent's small enough, just kind of counting your way around this cycle right here. I think I'll end this video here.